Dear student, thanks for holding on to these lectures in the module circulation. This is the mini lecture number 8, where I'm going to be presenting the concept of maximal oxygen uptake in relation to the situation when there are challenges to the cardiovascular system, where oxygen has to be delivered at higher rates than resting or normal. And of course, this is not a strange situation. There are many demanding situations in which oxygen has to be provided in larger amounts. Exercise is actually the one, training associated with exercise is the one that comes to mind for everyone, and this is the one that I will be discussing in this lecture. But then there are many other situations, independent on which animals, that can be highly demanding. Other activities can be more demanding even than exercise in species such as snakes, for example, snakes eating a large prey, or snakes that do incubate. Not all of them, a few species are able to do that, that incubate their eggs, and in order to do that, they have to shiver. And this constant muscle activity is very costly, and it puts a demand on the cardiovascular system in order to supply more oxygen. But this lecture will be essentially looking at exercise as a measure of performance and how oxygen is distributed, how oxygen can be distributed in higher amounts during these challenges. Let's look at some performance records in terrestrial mammals that some of you may be familiar with, some others may not. Take the example of cheetahs that can run at speeds of 113 kilometers per hour. Much faster than Usain Bolt can, for example. Feats in running endurance. Marathon runners will run 42 kilometers in roughly 2 hours at a pace of 20 kilometers per hour. If you have tried to keep a pace of 20 kilometers per hour and you're not particularly fit, you understand how difficult that is, and to do that for 2 hours. But then, of course, you have a mixture between the two, a mixture between speed and endurance, what I call here running performance. You see this, for example, in the American pronghorn antelope, an animal that can actually sprint or run for a long period of time, and it will do that in a rough terrain, high up in the mountains, for example, and at a certain speed, not as much as the cheetah, but certainly substantially faster than the 20 kilometers per hour in marathon runners. And then, of course, you have the scenarios, the situations of selected running performance in thoroughbred horses. Notice, for example, in the Kentucky Derby, the times there at around this race for 2 kilometers that will be run in around 2 minutes. That means a 60 kilometer per hour speed, and in this case carrying the jockey a load of an average 50 kilograms. So there are some of the feats that animals can endure. And if we take the first quickly, because that's not what the topic of the lecture is about, we take the cheetah, running fast. Fast running has nothing to do with aerobic challenge, and that's why I'm not going to extend on this in this lecture, because this is not what the lecture is about. In this case, the cheetah, being a fast runner, can do it because of different adjustments. First of all, something as simple as being the only feline without retractable claws, in terms of having a larger grip on the terrain in order to proceed faster. But of course, this is done as a sprint. The cheetah is a sprint runner. It cannot endure this speed for very long periods of time, because this run is powered mostly anaerobically, is powered mostly without oxygen. And the secret of this is actually in the muscle. In the muscle of the cheetahs, the combination of the biochemistry and the muscle composition makes the difference. First of all, the muscle in the cheetah has a high activity of lactate dehydrogenase and pyruvate kinase, which are the two key glucolytic enzymes. These are enzymes involved in glycolysis, in the production of ATP, without the need of oxygen. Muscle composition. If you see a cross-section of the leg muscles in the cheetah, what you see is a very high proportion of fast glycolytic fibers. These are fibers that actually operate with high levels of lactate dehydrogenase and pyruvate kinase, supplying ATP fast without the need to support or to provide oxygen. There are, of course, also slow oxidative fibers. The ones shown, they are much lighter. And they have a role in other activities, but not so much in the sprint performance. So, this is a nice feat, but it's not powered aerobically. The concept of VO2max, or maximal oxygen consumption, is actually a quantitative measure of an animal's capacity for the aerobic resynthesis of ATP, and thereby the ability to sustain high-intensity exercise for longer than a period of 4 to 5 minutes. In this case, what we are talking about is the maximum ability of transporting oxygen that will lead, of course, to the synthesis of ATP aerobically in aerobic conditions. This exercise can be sustained, unlike the cheetah, which is a short-lived exercise. And this is done classically using treadmills, or actually nowadays it can be done in many other ways, but essentially you have to provide an avenue for increasing the workload that an animal has to do. A treadmill classical, and treadmills have been used both in elephants and many other species, or in mice, basically using running wheels. The point being is that the animal is exposed to a set of successive increasing efforts, and oxygen consumption is measured simultaneously. While measuring oxygen consumption at increasing efforts, what's typically seen and what's expected is that for every new increased effort, oxygen consumption increases. The animal is able to use more oxygen and uses effectively more oxygen. But as we are getting close to the end, to the maximum ability of the animal to sustain exercise aerobically, what we see is characteristically that for an increased effort, eventually oxygen consumption, oxygen uptake will settle, will plateau. This is what we call the VO2max. Animals will not be able to continue running at higher efforts much longer than this, and certainly this would be the rule for oxygen consumption. What's happening then if the animal is doing more work at the same oxygen consumption, because it has reached VO2max, is that this will be done at the expense of anaerobic metabolism, of the production of lactate, which the consequent fatigue muscles that are running anaerobically will tire much faster, and this will be the end of it. So the idea of this type of testing involves animals running or performing exercise, whatever the exercise can be, and measuring oxygen consumption simultaneously. The RUF, the maximum oxygen uptake measure, is a measure of that particular individual ability to transport oxygen. Maximal oxygen consumption in humans is around 45 milliliters per minute per kilo. Of course, there is a big difference. There are big individual differences. Endurance athletes that train regularly can increase their VO2max above 70 milliliters per minute per kilo. And then we have the top athletes. This was for many years considered the maximum record of VO2max. Bjørn Dæhlie, a cross-country skier from Norway, which was basically measured VO2max between 93 to 95 milliliters per minute. Of course, there are many other casual observations of athletes basically performing close to this or even above this. It's not a matter of a record. The matter here is that basically the top athletes in some particular sports basically reach very high, more than double maximal oxygen consumptions. And this must obligatorily have something to do with their level of performance. It may not explain everything. It does not explain everything. A VO2 max will not determine how successful that particular athlete is. Biondelli won 12 Olympic medals, which is quite a feat in itself. But there must be more to it than the VO2 max, despite the fact that VO2 max will of course help. And this all has to do with the concept of the oxygen delivery cascade in the body. When we try to understand the physiology of this VO2 max, what we are saying is that we are looking at oxygen transport in the different stages by which this happens in the body. And of course, oxygen or air comes first in the lungs, and it has to be ventilated. Through gas exchange transports diffusion of oxygen and CO2 in the lungs. This oxygen will be taken into the circulation and eventually delivered to all the cells to the level of the mitochondria. So we have several steps in this cascade that are extremely important in understanding this. Oxygen flux through the ventilation, through the circulation, to the tissues, and finally for cellular metabolism. And it's important to realize that the ultimate VO2 max the organism is able to do will have to do with each one of these steps, how finely tuned they are to each other or not. What are the limitations to oxygen delivery during exercise? Obviously, during exercise you have new requirements for oxygen. The body has need for oxygen. This goes together with ATP. Oxygen is the fuel for ATP synthesis. These oxygen requirements during exercise can increase eightfold, can increase by eight times. Of course, larger energetic requirements might be necessary during burst activities, and then it's a question of distinguishing between anaerobic and aerobic. But ultimately, this can only happen if there is an increased flow through increasing pulmonary ventilation and increasing cardiac output. If there has to be more delivery to the level of the cells, there has to be more exchange in the lungs, and there has to be more transport in the circulation. So we should first look at these two steps and see where the limitations may be. The question we could pose is that, are these matched? Or is there one in particular that is limited? Take a look at what happens with pulmonary ventilation as oxygen consumption increases. Minute or total ventilation increases because of a simultaneous increase in breathing rate and tidal volume. Breathing rate, everyone understands what that means. Tidal volume is the amount of air per breath. Both of them increase during exercise. Unfortunately, what you see here in the graph is that there is a poor correlation between minute ventilation and VO2 max. That means that the total amount of air brought in and out of the lungs correlates relatively poor with VO2 max. And you see, to some extent, you see this here in this graph, because you have a good correlation with moderate exercises, but you see that the correlation is lost up here. There is a lot of scatter. To give you an idea of the range in changes that we see, basically, is that in resting conditions, the breathing rate may be typically around 12 breaths per minute, with a tidal volume of half a liter and a minute ventilation of 6 liters per minute. If you take this to vigorous exercise, the breathing rate can increase all the way up to 50 breaths per minute. The tidal volume may be up to 3 liters per minute and result in a minute ventilation of 150 liters per minute. So there is quite a dramatic change from 6 to 150. And notice, I want to emphasize this once more, how important it is that for breathing rate to increase from 12 to 15, from tidal volume to increase from half a liter to 3 liters. And I say this because my experience tells me that many students confuse these phenomena. There are many students that believe that when breathing rate increases, tidal volume decreases. And this is actually not true at all. with hyperventilation, with increased minute ventilation during exercise, breathing is faster and deeper, resulting in a large minute ventilation. Nevertheless, there is a poor correlation, or not a good correlation, between minute ventilation and VO2 max. If now we look at capacities in the lungs, or the volumes in the lungs, how they are distributed depending on the minute ventilation, you see that the higher the minute ventilation, basically the lower the reserve volumes, the higher the tidal volumes, as you would expect. But the point for this, with this slide, is that the scope for the increase in minute ventilation at the expense of reserve volumes is very large and unusually exceeded. So what you see is that even at the highest minute ventilations we see in this graph, there is still quite a large inspiratory reserve volume that is not achieved. This suggests that the lungs do not seem to be the limiting factors in performing exercise, in delivering oxygen. Because even at the highest minute ventilations, there is still plenty of reserve available that is not used. Could it mean then that the limitations lay in the cardiovascular system? Well, I guess we will see that. But first of all, let's try to wrap up the question about ventilation limiting aerobic power. First of all, in healthy individuals, the hyperventilatory response usually exceeds the needs of the organism, meaning excess capacity in the pulmonary system. Obviously, hyperventilation is associated with lower PCO2 and increased PO2 levels. But even during maximal exercise, a considerable breathing reserve exists, because minute ventilation at VO2 max usually equals 60 to 85% of the maximum voluntary ventilation. Meaning that at maximal exercise, we are still not using the pulmonary system at its max capacity. As a conclusion, ventilation is the least limiting system in hypermetabolic responses. I want you to notice something that it will be particularly relevant in the last lecture in this module, in lecture number 9. That, of course, maybe ventilation is the least limiting system in hypermetabolic responses, but it's also the one displaying the less plasticity, and that will become important. Let's look into increased blood perfusion instead. Is the cardiovascular system limiting? This is showing you the classical expression of the Fick's equation, basically saying that oxygen consumption is the product, if we look at the cardiovascular system, is the product of cardiac output, the amount of blood pumped by the heart per minute per unit of time, times the arteriovenous difference, the difference between the arterial and the venous blood. Cardiac output, of course, increases during exercise, and it does so by an increase in heart rate and an increase in stroke volume. Cardiac output is actually the product of heart rate and stroke volume. In athletes, cardiac output can increase 8-fold. In sedentary people, usually 4-fold is as much as it's achievable. So there is a consistent increase during exercise. And this is what you see here. Basically, in resting conditions, heart rate 50 beats per minute, stroke volume 100 milliliters, that means a cardiac output of 5. And in here, what you have is during exercise, a substantial increase in heart rate up to 195. Just a much smaller, much more modest change in stroke volume, and basically cardiac output in this case increasing 7-fold, a factor of 7. This is what you see here. As cardiac output increases during exercise, it does linearly because of heart rate increases, but stroke volume increases up to a point and then it stabilizes there, meaning that stroke volume becomes limited at high cardiac outputs, and it's mostly heart rate that drives this change in cardiac output. What's interesting is that if you correlate actually cardiac output and oxygen consumption with work output, there is an excellent correlation between the two. There is a very good correlation between oxygen consumption and cardiac output, suggesting that in this case, cardiac output would be the limiting factor for oxygen consumption. Actually, this is strengthened in this graph, because in this graph what we have, or what we can see, is basically a different groups of people. Endurance athletes in purple, sedentary college students in green, and then sedentary college students before training in yellow. So what you see is that essentially there is an important relationship here between oxygen consumption and cardiac output. And the main difference between the subjects is how far they are able to push this line. They all fall on a very similar line. The poorly trained, or the less trained you are, the sooner you fall in oxygen consumption and cardiac output. The more trained you are, the higher you can go. But this is in a tight relationship. Again, suggesting the same thing, a relationship between cardiac output and oxygen consumption, pointing to the potential role for cardiac output, or the main reason for cardiac output limiting oxygen consumption in humans during exercise. And this is the basic outcome of this. Oxygen consumption, maximal oxygen consumption, seems to be limited by the cardiovascular system more than by the respiration. To finish this mini lecture, I want to point out that it's not all about VO2max. Performance is driven by several factors. VO2max is one of them, but another important one is running economy. And also the fractional utilization of this VO2max. And this is important because we cannot use VO2max as a predictor of ultimate performance. We cannot actually predict the capability of someone winning races only based on this. There are many other factors that need to be studied, because that actually has been studied. What can explain the tremendous success that African runners have had for many years now in most important races, at the expense of other countries that are basically not succeeding in winning these races. When this has been studied, no apparent differences in VO2max have been observed. Kenyan runners do not have higher VO2maxes than other runners. Is it all in the running economy? It's in the fractional utilization. There are studies underway, and of course there are lots of different factors, maybe others that are not only physiological, that will account for this. But this is the end of this mini lecture. Thanks for sticking with me, and I invite you to continue in the last lecture in this module circulation, a lecture that I will be dealing with the topic of synmorphosis. Thank you for listening.